This is a course in trigonometry, but there are a lot of useful physics applications of these ideas, and so it's worth taking a little bit of time to talk about some of the physics ideas. In particular, we're going to focus on linear and angular velocities. Now, we're not going to get into a big argument about whether we mean velocity or speed here, because that's one of those physics subtleties that's not worth it for this class. But we are going to think about what we mean by this. So, a linear velocity. What do we mean by linear velocity? Well, think about going and driving your car, you're going 70 miles per hour. So 70 miles per hour. And if we think about that per, meaning like division, we could set this up as a fraction, 70 miles per hour. Now how many hours per 1 hour? And so this sets up this ratio, miles per hour, and we have 70 miles per hour. And so linear velocity is going to be this form. It's going to be a distance over a time, which we could write as d over t, or sometimes you'll see this as s over t, just depending on who's doing the writing. So this formula here sets up our concept of velocity. Velocity is a ratio of distance over time. What would an angular velocity look like? Well, an angular velocity, instead of thinking about distance, you're going to be thinking about angle, how much spinning you do in some amount of time. And so the way we write this is like this. Omega is equal to angle over time. And angle is typically denoted by a theta, so theta over t. This right here looks like a W. It's actually a Greek letter omega. And so some students will call it W. It's really an omega. It's a Greek letter. And that sort of keeps this consistent. So we have Greek letter here, and we use Greek letters for talking about rotations and things like that in this setup. Now this angle right here, something that's very important for this class, is that the angle we're going to use will always be in radians. We always want the angle in radians, and that will help simplify our formulas, and so we don't have to worry about chasing units around and things like that. If you're given the angle in terms of degrees or in terms of rotations, you're going to have to convert those values into radians. So 1 rotation is 2 pi radians. 360 degrees is 2 pi radians. And you use that conversion to make to convert the values for these problems. In some situations, the angular velocity and linear velocities are actually related to each other. The best way to think about this is to imagine a wheel. A wheel is spinning, but as it spins, that spinning translates into a linear velocity as it moves down the road or down the street or down whatever place this is traveling. And so there's definitely this relationship here. Now there's more to this relationship than just the rotation and the linear velocity, because the radius is going to matter. Let's call that radius 1, call that radius 2. Let's say that these wheels are rotating at 1 rotation per second. Which one is traveling faster? Well, in 1 second, this will do 1 full rotation, which is the distance is 1 full trip around the circle. And that distance around that circle is bigger than this 1 trip around this circle. Another way to think about this is to actually make the linear speeds the same and think about how this affects the angular speeds. So the linear speed, let's say that these two things are going the same linear speed. The smaller wheel has to spin faster to keep up with the bigger wheel. A non-circular version of this is to think about adults walking with little children. When an adult is walking, they have to take fewer steps relative to the little kids. The little kids have to move their legs a lot faster to keep up with the adults. And so this is another way of looking at this relationship between the size and the linear and rotational velocities. So here's what we have to do now. We have to figure out how these things are mathematically related. And so let's start with the linear velocity. So velocity is equal to how far it travels per amount of time. This s right here, if you think back to the example we just talked about, this s corresponds to an arc length. How far around this circle have you traveled in some amount of time? And so rather than using s, we can actually relate this back to the angle using the arc length formula. S is equal to r times theta. Right? And so now we have this setup. Velocity is r times theta over t. This ratio, theta over t, angle per time. That is an angular velocity. And so in fact, this is r times omega. And that gives us our fundamental relationship. Velocity is omega times r. And this relationship right here also captures everything that we said before. If we have the same rotational speed, but we have different radii, the bigger radius corresponds to a bigger velocity. If we have the same linear velocities, then the bigger radius has to have a smaller omega, and the smaller radius has to have a bigger omega, and that corresponds to the picture that we have up here. So these are how linear and angular velocities are related to each other, and this is the formula we're going to need to understand in order to do the problems. So here's a typical sounding example that mixes the linear velocity and the angular velocity. The high roller has a radius of 260 feet and completes one loop in 30 minutes. How fast in feet per minute does the ride move? So again, got a little Ferris wheel here, and let's say we start at the bottom, and it completes one full loop in 30 minutes. So 30 minutes for one loop. Now remember that for these problems, we want to be writing everything in terms of radians because that makes our formulas a lot simpler. So one loop, instead of thinking about one loop, we should think about that in radians. But one loop, one revolution is going to be 2 pi radians. And once we have this set up, we can think about the formula. Velocity, linear velocity is equal to angular velocity times the radius. So the radius we had was 260 feet. That's from the problem right here. And we just need to think through what the angular velocity is. Remember, angular velocity is the amount of rotation per amount of time. So the amount of rotation is 2 pi radians per amount of time. The amount of time is 30 minutes. And then we're going to also multiply that by the radius, which is 260 feet. Oops. If we think about the units here, remember that the radians are a pure unit. So in the final answer, they're not going to show up. And we have feet per minute, which is the exact same units we want in this problem. Feet per minute. And the rest is just to do the calculation. So 2 pi over 30 times 260. If we do some manipulation, we'll cancel out the 10. 2 times 26 is going to be 52. So it'll be 52 pi over 3 feet per minute. Now again, this value with pi written in it, this mathematical expression, doesn't really help us understand. So instead we're going to plug this into a calculator, and when you do, you get the value of 54.45 feet per minute. What does this mean? So every minute that goes by, the cart moves about 55 feet. And that answers the question. How fast does the ride move? The ride moves 54.45 feet per minute.